Welcome to SS2 Chemistry, Term 3, Week 10. Today we take a focused, deeper look at the contact process, the industrial production of sulfuric acid, the world's most important industrial chemical. Last week we covered the Haber process. This week we examine the contact process in full detail, including all three stages, the chemistry at each stage, the economic rationale for each condition, and the full range of uses of sulfuric acid. By the end of this lesson, you will describe and explain each stage of the contact process, apply Le Chatelier's principle to justify the conditions chosen, and answer all WAEC question types on this topic. Let us begin. Sulfuric acid, H2SO4, is produced in greater quantities worldwide than any other industrial chemical. Annual global production exceeds 250 million tons. It is sometimes called the king of chemicals because it is used in more industrial processes than almost any other substance. Nigeria imports sulfuric acid for its fertilizer industry. It is also essential for lead-acid batteries used in vehicles, which are critical to transportation across Africa. The contact process replaced the earlier lead chamber process because it produces much purer, more concentrated sulfuric acid. The older process could only produce about 70% H2SO4, while the contact process gives 98% pure acid. The name contact process comes from the contact of SO2 and O2 with the vanadium UV oxide catalyst surface. 3 industrial sources of sulfur dioxide. Source 1, burning sulfur, the simplest and cleanest route. SS plus O2 G, SO2 G, delta H equals minus 297 kJ per mole. Elemental sulfur is obtained from underground sulfur deposits, fresh process, hot water pumped underground to melt sulfur, then pumped out, or from petroleum and natural gas desulfurization, removing sulfur compounds to prevent pollution. Source 2, roasting metal sulfide ores, produces SO2 as a byproduct of extracting metals from their ores. For FeS2S, plus 11O2G, 2Fe2O3LS, plus 8SO2G, iron pyrite roasting. 2ZnS, plus 3O2G, 2ZnOS, plus 2SO2G, zinc blende roasting. The SO2 produced is captured rather than released to the atmosphere. Source 3, decomposition of calcium sulfate, gypsum 2-calcio4S, plus CS2CaO-S, plus 2SO2G, plus CO2G. Less common but used where calcium sulfate waste is available. The SO2 gas must be purified before proceeding to stage 2, it must be free of dust, arsenic compounds, and moisture, which would deactivate the catalyst. This is the critical stage and the one tested most frequently in WAEC. The reversible reaction, 2SO2G, plus O2G, 2SO3G, delta H equals minus 196 kJ per mole. Analysis using Le Chatelier's principle, the forward reaction is exothermic, delta H negative, so, increasing temperature shifts equilibrium to the left, less SO3, lower yield, decreasing temperature shifts equilibrium to the right, more SO3, higher yield. There are 3 moles of gas on the left and 2 moles on the right, so, increasing pressure shifts equilibrium to the right, fewer moles of gas, higher yield, decreasing pressure shifts equilibrium to the left, lower yield. Industrial conditions chosen, temperature 400 to 500 degrees Celsius, at 400 degrees Celsius, conversion is approximately 99.7%, at 600 degrees Celsius, conversion drops to about 74%. A temperature of 400 to 500 degrees Celsius is the compromise, high enough for an acceptable rate but low enough for a high yield. Without catalyst, even 1000 degrees Celsius would be too slow for commercial production. Pressure, approximately 1 to 2 atm, near atmospheric. Although higher pressure gives a higher yield, the yield at 400 to 500 degrees Celsius is already about 99.7%, making high pressure unnecessary. The equipment for high-pressure operation, compressors, high-pressure vessels, would be very expensive. The economic gain in moving from 99.7% to a marginally higher yield does not justify the cost. Catalyst, Vanadium V oxide, V2O5 lowers activation energy, greatly increases the rate at 400 to 500 degrees Celsius. V2O5 is regenerated in the process. It is a catalyst, not a reagent, operates via cycle where V5+ is reduced to V4+ and then oxidized back to V5+ by oxygen, poisoned by dust, arsenic, and water, hence gas purification in stage 1. Double contact process. In modern plants, SO3 is absorbed once, first contact, then the remaining unconverted SO2 passes over more catalyst, second contact. This achieves conversions above 99.9%, which is important both for yield and to reduce SO2 emissions. SO3 cannot be dissolved directly in water. If tried, SO3 plus H2O L, H2SO4 L. This reaction produces an extremely dense, fine acid mist which is very difficult to contain. It forms a stable aerosol that floats in air, cannot be condensed easily, escapes from equipment, and is both hazardous to workers and damaging to the environment. Instead, SO3 is absorbed in concentrated sulfuric acid, 96 to 98% H2SO4. SO3 plus H2SO4 H2S2O7 The product H2S2O7 is oleum, fuming sulfuric acid, also called pyrosulfuric acid. Oleum is then diluted carefully, slowly, with cooling, with water, H2S2O7 plus H2O 2H2SO4 The overall process from SO3 and water, SO3 plus H2O H2SO4. Uses of sulfuric acid, production of fertilizers, most important use, reacts with phosphate rock to make superphosphate fertilizer, Ca3PO4, 2 plus 2 H2SO4 Ca, H2PO4, 2 plus 2 CaSO4, reacts with ammonia to make ammonium sulfate, 2 NH3 plus H2SO4 NH4, 2 SO4, manufacture of other acids, dilute H2SO4 plus NaCl HCl, H2SO4 plus NaNO3 HNO3, lead acid batteries, the electrolyte is dilute H2SO4, 30 to 38%, detergent and surfactant production, petroleum refining, removing impurities from crude oil, dyes. Explosives, TNT, nitroglycerin via nitration using mixed H2SO4/HNO3 acid, synthetic fibers, rayon, nylon processing, metal pickling, removing oxide layers from metals before electroplating or galvanizing. Key points. Contact process produces sulfuric acid, H2SO4, the world's most produced industrial chemical. 3 stages. Stage 1, produce SO2, burn sulfur or roast sulfide ores. Stage 2, oxidize SO2 to SO3, 2SO2 plus O2 to SO3, catalyst V2O5, 400 to 500 degrees Celsius, near atmospheric pressure, yield 99.7%. Stage 3, absorb SO3 in concentrated H2SO4 to form oleum, H2S2O7, then dilute with water to give H2SO4. Why not add SO3 to water directly? Forms uncontrollable acid mist. Stage 2 conditions explained by Le Chatelier. Exothermic, so lower temperature gives higher yield, but 400 to 500 degrees Celsius chosen for reasonable rate. Atmospheric pressure acceptable because yield is already very high. V2O5 catalyst lowers activation energy and makes 400 to 500 degrees Celsius commercially viable. Major uses: fertilizers, batteries, making other acids, detergents, metal processing. WAEC frequently asks students to write the equation for stage 2, state conditions and justify them with Le Chatelier, explain why SO3 is not dissolved in water, and list uses of H2SO4.